Okay.
Hello and welcome everyone to Iris Biotech's second online workshop. True to our slogan, Empowering Peptide Innovation, we are keen on knowledge exchange and getting in contact with scientists all over the world, which is why we started this workshop series mid of this year. Today, the main topic is the prevention of aspartimide formation, surrounded by some brief introductory information on the company Iris Biotech. My name is Raimund Meyer. I am working as a project manager at Iris Biotech, and today I will guide you through this online workshop. If you wish to announce your participation on social media, please feel free to use the hashtag Iris Workshop Series, which is also displayed right now in the Microsoft Teams chat. To have a pleasant experience for all participants, I would like to begin with some technical guidelines. To ensure the best possible audio and video quality, all participants are automatically muted and your video camera is switched off. Another important information is that this live event is recorded. Thus, if you enter late or miss anything, please check on the bottom left side of your Teams screen if you are watching the recording or if you are live, which is shown by the red broadcasting symbol. You have the possibility to pause the video, rewind, or jump back to the live session. In addition, the recording of the workshop will be uploaded on our homepage afterwards. Questions can be submitted by using the Q&A chat of Microsoft Teams. You can enter your name or submit your questions anonymously. We will frequently check the questions, publish them, and submit them to the respective speaker. If you have any technical queries, you can also submit them in this Q&A chat. Our technical assistant will then connect with you and try to solve the problem. Initially, the questions are just visible for the organizers and will then be published to the audience. So don't worry if your question takes a short moment to appear on screen. To try out the Q&A chat, we will now post a question which you can answer. Now you should see the question, what is the topic of today's workshop within the chat? Please feel free to answer to try out this tool. Okay, so finally it seems to work. Now answers are coming in. Okay, fine. Yes, the correct answer is, of course, the prevention of aspartimide formation. So, as this finally seems to work, I would like to quickly guide you through today's agenda. We will start with a short company and topic introduction by our project manager, Markus Weishaupt. Afterwards, our external speaker, Professor Jeffrey Bodie, will provide detailed information on his research at the ETH Zurich and his building blocks to prevent aspartimide formation. As mentioned, questions will be collected throughout all talks in the Q&A chat and are forwarded to the speakers. Of course, you can also get in contact via email or phone call after the workshop. One last note from my side, if you accidentally close your Microsoft Teams window, don't panic. You can just relog in, and as the workshop is also available as recording, you will not miss anything. After this quick technical introduction, let's continue with the first agenda point, an introduction to our company and to the topic aspartimide formation by our project manager, Markus Weishaupt. Markus studied biochemistry at the University of Bayreuth and obtained his PhD at the Max Planck Institute in Berlin in the field of solid phase organic synthesis. In 2015, he joined Iris Biotech as a project manager. Markus, thank you for your valuable time. Please go ahead with your presentation.
Thank you, Raimund, for your kind introduction. As Raimund already mentioned, I would like to start off this brief introductory presentation with some words and information about our company, Iris Biotech. As some of you may have noticed, we recently changed our company logo to a more contemporary design. The catalyst for this change, so to speak, was the fact that this year marks the 20th anniversary of IRIS Biotech's founding. Our roots go back to the chemical factory Marktredwitz, which was in fact the very first chemical factory in Germany, founded in 1788. Since our founding in 2001, IRIS Biotech has shown a steady growth. We have established our own production in the southwest of Germany. And in 2018, we moved to our new company headquarters in Marktredwitz. Our product portfolio currently comprises roughly 7,000 products. Although we are best known as provider for everything related to peptide chemistry, we also have a strong presence in other fields such as life sciences, drug delivery, or linkerology, to name just a few. We inform our clients about new products and existing products in our bi-weekly newsletter, the blog posts of which you can find in our knowledge base alongside booklets on some of the topics listed above, as well as specialized topics. We provide our products, most of our products, starting from gram or lab scale quantities through pilot scale up to bulk quantities for commercial productions. Of course, always alongside the necessary documentation. True to our motto, empowering peptide innovation, we constantly develop our portfolio and keep adding new products, new innovative products at a rate of over 50 products per month. One of those innovative products will be shown in more detail later in this presentation. So now to the chemical part, a brief introduction of aspartimide formation. So aspartimide formation is one of the best documented, if not the best documented, side reaction in peptide synthesis. This is not surprising since it results in low yields and usually necessitates laborious purifications and may even render certain peptide sequences inaccessible by chemical synthesis. The rate of aspartimide formation is influenced by various factors, for example, pH and solvent. It is also strongly sequence dependent. For example, if the amino acid preceding the aspartate residue is a glycine, asparagine, aspartate, or cysteine, this strongly favors aspartimide formation. Over the years, several strategies to avoid the side reaction have been developed. For example, the use of dipeptide building blocks, where the peptidic bond between the aspartate and the preceding amino acid is already formed. The addition of certain compounds to the reaction, to the deprotection mixture, such as HOBT or oximapure. The addition of various new aspartate side chain protecting groups to the chemist's toolbox, as well as the introduction of certain protecting groups for the alpha amino group. However, some of these methods may not fully prevent aspartimide formation and may cause other difficulties during synthesis. One example is that bulky protecting groups may render the synthesis of cyclic peptides very inefficient. So how does aspartimide formation work? It is promoted by bases, for example, piperidine. As piperidine is used in most FMOC deprotection protocols, this is of course a problem which is exacerbated with each FMOC deprotection cycle. Furthermore, the side product formation does not stop at the aspartimide, but further byproducts arise from the nucleophilic ring opening of the aspartimide, depending on which nucleophile attacks and on which carbonyl. This leads to several byproducts. if the nucleophile in question is water, you will end up with racemized alpha peptides and beta peptides. If the nucleophile is piperidine, depending on where it attacks, on which carbonyl group, you will end up with racemized piperidides of the alpha or beta peptides. As already mentioned, this decreases product yields and necessitates time and cost-intensive purifications. Of course, there's also the issue of co-elution, especially when looking at longer peptide sequences. The retention times of some of the byproducts here are almost indistinguishable from the desired product. Of the possible solutions previously mentioned, I would focus on one, that is side chain protecting groups. So one obvious solution is to just increase the steric bulk of the aspartic acid ester protecting group. This works by shielding the beta carboxyl group from nucleophilic attack of the neighboring alpha amino group. The principle basically is the bulkier, the better. So the bigger the protecting group, the better it is at attenuating aspartimide formation. However, the steric bulk and the hydrophobic nature of the protecting group may lead to other problems during synthesis. One novel approach to protect the side chain of the aspartic acid residues is to mask it as a cyanosulfurylate, or CSY. This approach was published by the Bode group recently in Nature Communications. When looking at the CSY group, one striking difference to the protecting groups shown on the previous slide is that here, instead of the label ester bond, you have a stable carbon-carbon bond. Consequently, the CSYs are stable towards strong acids and strong bases, as well as many oxidative conditions and radicals. Nevertheless, it can be selectively and quantitatively cleaved under aqueous conditions with electrophilic halogen species such as N-chlorosuccinimide. The Zwitter ionic CSY shows enhanced solubility compared to bulky ester protecting groups. And as CSYs are strongly absorbing at 254 nanometers, cleavage can be monitored by HPLC. So all of these advantages were so exciting for us that we decided to contact Professor Bode and ask him whether he would be willing to commercialize this building block together with us. And fortunately, he agreed to this collaboration. So now the corresponding FMOC building block is a regular product at Iris Biotech, and you can find it on our website. I don't want to go into any more details regarding this building block, as I'm sure you will hear more about its properties in the next presentation. And I will close with a brief summary. So aspartimide formation is a very well-studied side reaction. However, it may still be difficult to tackle despite decades of research on the topic. Every solution comes with its own drawbacks, so there's no one-size-fits-all solution so far. However, the cyanosulfurylates to mask the aspartate side chain offer an innovative new way to tackle aspartimide formation. So with this, I would like to close my presentation. I thank you for your kind attention, and if there are any questions, I would be happy to take them.
Okay, thank you, Marcus. Thanks for this introduction to the topic. If you have any questions to Marcus, please type them in the Q&A chat. By now, we have received one question. Marcus, does aspartimide formation also occur when you're applying the Bock synthesis strategy?
Yes, indeed it does. However, the problem is more pronounced when applying the FMOC strategy.
Okay, thank you. By now, I do not see any further questions. We will forward questions if they would come up within the next minutes. Thanks again, Marcus. And now, after this introduction, let's go on with the highlight of today and switch to the external presentation. It is my pleasure to introduce to you Professor Dr. Jeffrey Bodie, Principal Investigator at the ETH Zurich in Switzerland. Jeffrey studied chemistry and philosophy at Trinity University in San Antonio, Texas, where he worked in the research group of Professor Michael Doyle. After PhD studies at the CIT in Pasadena and at the ETH Zurich with Professor Eric Carrera, he spent 2 years in Japan as postdoctoral fellow with Professor Keisuke Suzuki at the Tokyo Institute of Technology. And in 2003, he began his independent career in the US, first at the UC of Santa Barbara and then at the University of Pennsylvania. And then in 2010, he moved to the ETH in Zurich, Switzerland, as a full professor in the Laboratory of Organic Chemistry. Since 2013, he is also a principal investigator at the University of Transformative Biomolecules at Nagoya University, Japan, where the Bodie Group has a satellite laboratory. Jeffrey, the stage or video platform is yours. We are looking forward to hearing about your recent research, and for the audience, please post your questions by using the Q&A chat during Jeffrey's presentation.
Thank you, Raymond, for the very kind introduction and the invitation to come here today and talk a bit about our chemistry. So I will just try to start my presentation. Okay, very good. So I will start by talking a bit about what we do in our group and how we became interested in the problem of aspartimide formation, and then discuss a bit about our sulfur ylide-based solutions, and show you a few applications of some quite complex peptide and protein domain syntheses that we can do using these new aspartimide preventing protecting groups. So our group is largely interested in the chemical synthesis of proteins. And to do this, we take advantage of really the fantastic technology of solid phase peptide synthesis. So I guess many or most people in the audience are very familiar with this. And nowadays it's quite common, quite predictable to be able to make peptides up to about 50 amino acids and sometimes even beyond. And so we really want to take advantage of the innovations that have come from generations of peptide chemists to develop this really fantastic technologies, particularly FMOC solid phase peptide synthesis. So we push this to the limit, and we typically synthesize peptide segments around 40 to 50 amino acids. At this point, we've usually reached the limit of what we can do as a single segment. So we cleave these from the resin, and we isolate and purify the peptide segments. And then to prepare longer structures, such as proteins, we need to combine these segments together. And for this, we use chemoselective ligation reactions. So the idea is really that we will have these purified, fully deprotected peptide segments, and then link together the C and the N terminus of two different segments to form longer structures. And then ideally iterate that so that we can access even larger targets. And as an organic chemist, I was really fascinated by this problem because it is a question of chemoselectivity. right? We need to identify 2 different functional groups or moieties. We need to install those into the C and the N-terminus of the peptide segments. And then those functional groups need to come together and chemoselectively form an amide bond. And this needs to happen in the presence of all of the unprotected side chains, such as carboxylic acids, amines, thiols, alcohols. For the most part, this chemistry should be at least somewhat compatible with water. It should preserve the stereochemistry in the peptides, particularly at the ligation sites. And ideally, of course, we would want this to form an amide bond. There are very powerful chemoselective reactions out there, but most of them do not form amide bonds. So this question of what functional groups can we have on the peptide segments in order to perform chemical ligation reactions has been investigated by many groups, and there are several very good solutions. So the most famous and most widely used one is the native chemical ligation developed by Stephen Kent and his co-workers. And this utilizes C-terminal thioesters and peptides that contain an N-terminal cysteine to give this ligated product here. And this works very well under aqueous basic conditions. There is what's called the serine-threonine ligation, which utilizes this special C-terminal ester and a peptide that contains a serine or threonine at the N-terminus. And that leads to this intermediate that can be decomposed into the ligated product. There's some really beautiful and powerful work using enzyme-mediated ligations, such as sortase, as shown here. And then there's work from our group that I will talk briefly about today, which is what we call the CAHA ligation or alpha keto acid hydroxylamine ligation, in which one peptide contains a C-terminal alpha keto acid and an N-terminal hydroxylamine, and we can combine these peptide segments together under acidic conditions in order to form the amide bond. So the CAHA ligation is a reaction we identified quite a while ago, and it's really a very simple reaction. If you have an alpha keto acid and hydroxylamine, you can combine these together in a polar solvent, such as DMF, DMSO, in many cases water. It works best under acidic conditions. So we typically run these around pH 2, pH 3, which is really ideal for solubilizing unprotected peptide segments. And this results in an amide bond. And there's actually several different mechanisms for the CAHA ligation, depending on what type of hydroxylamine that you have. So if we have an OH group, we call it a type 1 ligation. And then depending on the R group here, acyl or alkyl, it can undergo either a type 2 ligation or a type 3 ligation. All of them proceed first by addition of the hydroxylamine to the keto acid to form this tetrahedral intermediate. And in the type 3 ligation, this goes to an iminium species, which undergoes decarboxylation to this nitrilium, which is then trapped to give the amide bond. In the type 2 ligation, which we don't really use too much in our group, there's a direct concerted decarboxylation and cleavage of the NO bond to form the amide directly. But in the context of protein synthesis, we faced immediately this challenge of being able to effectively prepare peptides containing a C-terminal keto acid or peptides with an N-terminal hydroxylamine. And we really wanted the technology for making these peptides to be compatible with FMOX solid phase peptide synthesis. We wanted to use the same resins, the same coupling reagents, the same monomers, the same HPLC protocols that people are familiar with. And to do that, we had to essentially develop our own chemistry, our own way of accessing the keto acids, our own linkers that can be installed onto standard resins, our own special hydroxylamine monomers with suitable protecting groups. And you see a long list of PhD students and postdocs who, over the course of about 5-6 years, really worked very hard to solve these problems. And by and large, these problems have been very effectively solved by a really outstanding team of co-workers. So for the keto acids, the first thing to note about the keto acids is that once you know how to make them, they're really beautiful compounds to work with. They're quite stable. You can treat them just like you do any other peptide. You can purify them by reverse phase HPLC. You can lyophilize them. You can store them. So they're really quite easy to handle. They do not epimerize. You have to really work very hard to epimerize them. The challenge at the beginning was to make them. And to do this, we adapted some chemistry originally from Harry Wasserman using phosphorus ylides. And we eventually found that sulfur ylides worked much better, and we can take any standard FMOC protected amino acid. We can activate that with any standard coupling reagent. Here we use T3P. And allow that to react with this ylide precursor to form this what we call cyanosulfur ylide. These are exceptionally stable compounds. They are completely resistant to protonation, to strong acids, to base, but they will undergo an oxidative cleavage with oxone to deliver the alpha keto acid. And this is very reliable chemistry that has been done on gram scale, and I believe now kilogram scale as well. And once we have the keto acid, what we need to do is protect it so that we can incorporate it onto a standard resin. And we do this with a specially designed protecting group. So we have this kind of diol with an aromatic group here. And we can form this protected keto acid that is acid labile that will cleave with TFA. And we can also form these photolabile ones, protected version that is stable to TFA but can be removed with light. And so once we have these protected amino acids, we can couple them onto a resin or install a linker and couple that onto a resin. And from this point forward, everything is just standard FMOC solid phase peptide synthesis. We can do this, for example, on an automated machine. And then when we cleave the peptide with TFA, we get directly the keto acid, and all of the side chains are unprotected. And we can make many different protected keto acids. So those, we typically use leucine just because it is such a common amino acid, but also phenylalanine, tyrosine, valine, and many others we can form as well. And the photoprotected one is also very useful for us in the context of protein synthesis, because here we can leave the keto acid in protected form, and then later on at a separate point in the synthesis, use photolytic conditions to remove the protecting group and reveal the keto acid. For the hydroxylamine, we had some more challenges. So not all of them are stable, and some that are stable are not easy to make. And for the most part, we eventually settled on using this, what we call 5-oxyproline. This is very easy to make by a catalytic and antioselective route. It is completely stable. It's basically just like proline. We can protect it in many different ways, and we never see any decomposition, any premature cleavage of the NO bond or anything like that. So as long as we can get away with using this one, it introduces a homoserine at the ligation site. We typically use this. If there's particular considerations where we need a natural residue, we will use some of the fancier ones where we can introduce aspartic acid or threonine or glycine residues at the ligation site. And the other reason we really like this oxyproline is that unlike most of the other monomers for for CAHA ligation, it actually forms an ester rather than an amide during the ligation. So very surprisingly, this was not something that we had expected. If we perform CAHA ligation with any kind of keto acid and this 5-oxyproline, the primary product is an ester. And this really helps us if we are synthesizing very hydrophobic proteins. So we can keep our growing protein in this ester form. This helps immensely with solubility and handling. And then at the very end, typically during the folding of the protein, we expose this to basic conditions, usually somewhere between pH 8 and pH 10, and this ester undergoes an O to N shift to deliver the amide. And so using this technology, we can prepare quite a few proteins. I just show 2 examples today. So one is from insulin. So we can prepare 2 segments of insulin. This was a collaboration with Sanofi in Frankfurt, and they helped us design this linker, which was actually in the old literature. So we can prepare the A chain with this linker, this prosthetic C peptide, and then a little bit of the B chain and an oxyproline, and then a B chain with the keto acid. And we simply combine those together under CAHA ligation conditions, which are typically DMSO water. That gives us here the DEPC peptide, and then we remove the ACM side chains from the A chain and B chain, and then expose this to folding conditions, which results in removal of the C peptide and then formation of the 3 disulfide bonds to give us the fully assembled insulin. And this is a typical CAHA ligation. These are the 2 starting materials. This is the product being formed. After overnight, we see mostly the product. We can purify that and then put this through to the folding and excision conditions to give the purified insulin. And likewise, if we're making longer proteins such as interleukins, we typically assemble this from 4 segments. So we prepare these 4 different peptide segments, again, typically around 40 amino acids each. We have a protected keto acid, a protected hydroxylamine. We perform the CAHA ligations, and then in the same reaction, we remove the protecting group here by light and here by base, and we purify those segments and then do a 3rd CAHA ligation to give us the fully assembled protein containing the 3 ester bonds, and then remove the ACM groups and subject that to folding to give us the fully assembled folded proteins. And this technology is very scalable. It is the basis for a biotech company that has been spun out of our lab, in which we use CAHA ligation to prepare fully synthetic therapeutic proteins such as cytokines. And now we are basically at the manufacturing stage of quite innovative therapeutic proteins which contain a couple unnatural residues which we can use to both improve the biological properties and perform half-life extension. So with this technology established, we really can make lots and lots of proteins. We've made dozens of proteins and on substantial scale. The bottleneck is still making the peptides. So once we know how to synthesize a peptide, it works very well. Yeah, and we can scale that up to grams or even hundreds of grams. But it still can be very challenging to work out the conditions for making the peptides, particularly if we need to do this on substantial scale. And so we have our site in Zurich, and we have a satellite lab in Nagoya, which also focuses on peptide synthesis. And now we have also Bright Peak, which is based in Basel. So having these different aspects of the group or spinouts has allowed us to make a lot of mistakes and learn the hard way, you know, how to do peptide synthesis and how many things that, you know, can go wrong and how to fix them. And as Marcus alluded to, one of the biggest challenges in making longer peptides is aspartimide formation. So if we look at for example, a peptide that we were interested in making that has these 3 aspartic acids here, if we just use our standard conditions for FMOX solid phase peptide synthesis, we end up with a crude peptide that looks horrible, that looks something like this. And this is again due to the formation during the peptide synthesis of aspartimide and then ring opening of this aspartimide to give us these adducts and epimers and beta peptide analogs that just really complicate the synthesis of certain peptides. And we, of course, use all of the different solutions that are out there, the more hindered esters, or what we particularly like when it's feasible is to use backbone protection. This is definitely a very effective way of preventing aspartimide formation, but it is not suitable for all cases where aspartimide formation happens. And in particular, we were really struggling with this while trying to make a certain type of protein domain called LA domains, which have 3 disulfide bonds and really a very high number of aspartic acid residues. And this is where we came to the idea of saying maybe we can take some of our experience in making the keto acids, in which we have introduced a carbon-carbon bond, and use that to completely prevent aspartimide formation. So the idea was to go back to our sulfur ilids, which we know to be remarkably stable and very easy to make, and see if we could come up with different cleavage conditions that would eventually give us the acid, right? So we had typically used these sulfur ilids and treated them with oxone, which delivers the alpha keto acid. But what we want to do is actually to get the carboxylic acid instead. And so we eventually realized that we could do this by using an electrophilic halogen source. So I show just a very simple model substrate here. So if we have this type of sulfur ilid and we treat it with NBS, in just 1 minute, we see cleavage of the sulfur ilid to give us the carboxylic acid. The mechanism is quite interesting. It's related to the haloform reaction. So what happens is the sulfur ilid is chlorinated by the electrophilic chlorine. It forms this intermediate, which hydrates and then breaks down by cleavage of this carbon-carbon bond to give us the carboxylic acid. And so knowing that, we thought, okay, maybe we can just install this into a aspartic acid monomer. And that's quite simple to do. We just take this side chain unprotected aspartic acid monomer. We introduce the sulfur ilid using our standard method for that and remove this terbutyl group to form this aspartic acid monomer, which we can then incorporate by solid phase peptide synthesis. And so if we just take a very simple model peptide with the terbutyl group here and incubate that with piperidine, what we see is it very quickly becomes messy via the intermediacy of aspartimide. However, if we take our sulfur ilid variant, we can incubate this overnight with 20% piperidine, and we don't see any breakdown of the cyanosulfur ilid. This is a completely stable peptide. And so we can then incorporate it into longer sequences and examine cleavage conditions. And again, using a very rapid reaction, so NCS in aqueous acetonitrile at pH 3, it takes just a couple minutes to cleave the sulfur ilid to the carboxylic acid. So this is the starting material here with the sulfur ilid, and this is the cleaved one, which is now the free carboxylic acid. And so with that established, we went back to these targets that we were interested in, these LA modules, which are known in the literature to be very difficult to make due to the prevalence of aspartimide formation. And sure enough, when we tried in our hands the synthesis of this, we see this very messy trace from the solid phase peptide synthesis. when we put instead these sulfur ilids, we see a quite clean trace, and we can purify that to give us the peptide containing the sulfur ilid. And if we take that, so here we have 4 of these cyanosulfur ilids. We cleave this with NCS. It takes about 20 minutes in aqueous acetonitrile. And we see a nice crude trace. We can purify that. And then in this case, we used S-tert-butyl protected cysteines. We can remove those with TSAP and then fold this domain quite cleanly into the folded structure with 3 disulfide bonds. So this worked very well, and we applied this to a number of different model peptides and protein domains, as published in Nature Communications last year. So we were quite happy with this, but for some of the work that we were doing, we still recognized quite a few limitations. So one is the NCS is not compatible with ACM protected cysteines, and we typically like ACM protected cysteines. The CAHA ligation is compatible with unprotected cysteines, but we typically leave them ACM protected just to facilitate the handling of the peptides, particularly when we have many of them. If we are using oxoproline in unprotected form, and the NCS will also oxidize the oxoprolines, and NCS and methionine also do not get along, and so we typically need to mutate the methionines to norleucines if we are cleaving with NCS. And so for some of the small domains, this was fine, but we were also interested in dimeric or even longer LA domains, and we wanted to assemble those using CAHA ligation, and that required us to work with the unprotected oxoproline, and we also wanted to go back to using the ACM protected cysteines. And this led us to look for an alternative to the sulfur ilids. So what we thought is, the way that this cleavage works is that we have an electrophile which reacts with the sulfur ilid. And so if we could have a little bit more reactive sulfur ilid, then we could use a proton instead of an electrophilic halogen source, and that could reversibly protonate the ilid. And if we could get a substantial proportion of this keto form, it should be able to hydrate and break the carbon-carbon bond to give us the unprotected carboxylic acid under acidic conditions. And we looked into quite a few different candidates, and the one we eventually chose to develop further is these pyridine ilids. They're also very easy to form and quite stable, and they can be cleaved back to the carboxylic acid under aqueous acid. So we took that information, and again, we took the unprotected aspartic acid, we installed the this what we call a SciPi or cyanopyridinium ilid onto the side chain. And here we need to be a little careful how we deprotect this tert-butyl group, because under acidic conditions you can cleave this ilid, but with zinc bromide or with dry TFA, we can cleave the tert-butyl group and produce this monomer. And then once again, we showed just in this model peptide that with standard tert-butyl protected aspartic acid, we get decomposition, but with the cyano ilids, we can see very clean formation of that peptide, and we can also cleave it under aqueous acidic conditions. And so with that, we started to prepare some of these more demanding LA modules. So here's one with 5 aspartic acids. We protect all of them as the cyanopyridine ilid. This is just standard peptide synthesis, standard resin cleavage conditions. And then after the resin cleavage has finished, we add aqueous acetonitrile and aqueous HCl and incubate that for an additional 2 hours. So this is the crude peptide with the cyanopyridine ilid present, 5 of them, and this is what it looks like after we cleave and purify. So we can get really nice looking peptide. And then from here again, we can do ACMD protection with silver and then expose that to folding buffer and isolate the folded LA module. And the mechanism is exactly as I said. It's protonation to give this keto form, hydration, and then a haloform-like carbon-carbon bond cleavage reaction. And so to do ligations, we prepared now these segments. So we picked 2 of these LA domains, which come together, LA4 and LA3. We prepare those again with the cyanopyridine ilids. They're not, perfect, but we see pretty good looking crude peptide, certainly a lot better than the one we made with the tert-butyl protected aspartic acid. And we can get this, this is the fully deprotected one. We can get this quite pure in the end. And same thing for the other segment. And so taking these segments, now all of the aspartic acids are cleaved to the carboxylic acid. We just have the ACMs protected. We can perform the CAHA ligation and then O-N shift. So here's the start of the ligation. This is the ligated product. This is the O-N shift, and this is the purified dimer now. And then remove the ACM group and then subject this to folding to give us the isolated folded dimeric domain. And so we've made several of these now. We see really beautiful characterizations by mass spec. And we're working now with a group in Copenhagen to do some biological studies using these assembled LA domains. So I think I'm coming to the end of the talk. And again, we identified these 2 variations of cyanoilids, so the cyanosulfur ilids. These are very, very stable, easy to make, and can be cleaved in the presence of an electrophilic halogen source, particularly NCS, under aqueous acetonitrile conditions. And we use that for making some of these single LA modules. For cleaving under acidic conditions, so directly after resin cleavage, we use these pyridine ilids. And so we can apply those to a little bit more advanced protein synthesis, including performing CAHA ligation, using systems that are compatible with the monomers and the ACM protecting groups that we like to use for these larger segments. And as Marcus mentioned, so Iris has been very kind to make the cyanosulfur ilid variants of aspartic acid already commercially available. And we're working together now to make the cyanopyridine variants available as well. And again, just to mention CAHA ligation, it's really a very easy way of combining these longer peptide segments together under acidic conditions, which is really great for solubility. We don't have anything else in the reaction, so it's very simple. We can just take these ligation mixtures, put them directly on the HPLC, and purify this. We don't need to worry about buffers or salts and things like that, and get to these longer protein or longer peptides directly. And for all of this, I'd like to thank my research group. They've done a really fantastic job of pushing this technology forward. And in particular to Dr. Kevin Neumann, who who recognized that we could use the sulfur ilids for addressing this aspartimide problem, and really, challenged this by identifying extremely difficult peptides that we could not make with standard methods, and demonstrating that this chemistry could address that problem very effectively. He's now left my group and has started his own research group in Nijmegen. So, and again, thank you to Iris for the opportunity to talk to you today, and I'd be happy to answer any questions.
Thank you very much, Jeffrey, for sharing those interesting results with us, for taking us on this journey through long years of research. During your talk, we collected some questions. Some of them were already at least partly answered, but I will repeat them nevertheless. So what first came up is in context with the CAR ligation, how stable are the keto acids during the cleavage, and are there any recommendations to remove, for example, TIS from cleavage solution to avoid reduction of the keto group?
Yeah, that's actually a very, very good point. So the keto acids are stable, but we do not use silanes during the resin cleavage. So we use other scavengers. If you use TIPS or TES during cleavage, you can reduce the keto acid to the alcohol. So yeah, please avoid that.
Okay, and two questions that go a bit in the same direction, and you already, in fact, answered those. The one is, will amino acids or protecting groups that are sensitive to oxidation be affected by the deprotection conditions for CSY? That's what you already pointed out, for example, with methionine, and something in the similar direction. What is the compatibility of CSY with electron-rich aromatic amino acid residues?
Yeah, that's a very good question. As far as we can tell, it's compatible with tryptophan and tyrosine. So the NCS conditions seem to be rapid and mild enough that we can do the CSY deprotection in the presence of the other aromatic amino acids. It's really just methionine that's a problem. And ACM protected cysteine, you can probably get away with it, but you can definitely see some modifications from time to time. Interestingly, the S-tert-butyl, so the S-tert-butyl modified cysteines are completely stable to the NCS conditions.
Yeah, that question even came up once more. Is NCS compatible with tryptophan and other electron-rich aromatic residues? Just answered. How about the new protecting groups compatibility with microwave-assisted oxima and DIC solid phase synthesis?
Oh, that's a good question. I'm not sure. We do not typically use microwave peptide synthesis in our group, but I don't really see why they would not be compatible, but I would definitely want to test that at some point.
Mm-hmm. Okay.
The CSY for sure should be compatible. I don't see any problem there. The pyridines, we would have to test.
Mm-hmm. Also, then one practical question, was the purification done by C18 reversed phase HPLC, or did you have to apply more complicated purification procedures?
Typically not. We typically use C18 for almost everything. Once in a while, we will use a C4 for a particularly hydrophobic segment. But by and large, we use just really standard purifications and columns for all of the keto acids, the CSY protected side chains. There's nothing special that you need to do compared to normal peptide purification.
So the next question is, what about aspartimide formation during the chemical ligation of unprotected peptide segments?
We have never seen that. That's a very good question. And, so we do the ligations under acidic conditions. So it's typically pH 2. Many years ago, we worried really a lot about deamination or things like this, for example, asparagines going to aspartic acids, and that is not something that we have ever observed, even upon looking for it. The ligation conditions with DMSO, and you can use a number of acids. We typically use oxalic acid because it seems to work well and doesn't damage our HPLC columns. It really seems to be beautiful. You can get quite high concentrations of peptides under those conditions, and they seem very happy. So we don't see any problems there. Yeah.
Okay, so and one last question, is the homoserine peptide stable in the acidic conditions, or can there be a 5-membered ring formed with the C-flanking amide?
So you can, but you really need to work at it. So something like 2 molar HCl for an extended period of time. The homoserines are remarkably stable. That's a very good question that we have also looked into. They're not like homocysteine residues where you can see cleavage. You do not easily cleave a homoserine residue. We have, again, with very, very strong aqueous acid, we have actually used homoserine cleavage to break down some very hydrophobic peptides that were resistant to trypsin for proteomic studies. But that's really the only case where we have been able to cleave it, and it took some work to do that.
Okay, so there seem to be no more questions. I see one question was whether the ASP-CSY is also available as D-isomer. Marcus already answered in the chat. Yes, of course, we have both the L and the D-isomer. And yeah, currently we're working on making available also the SciPy versions. Jeffrey, thanks again. It was a pleasure to have you as our external guest expert, and it was really great to see what is possible and also to see how difficult it is to come to a good result. So as currently we do not see any further questions within the chat, of course you always can ask more questions. Don't hesitate to contact us by email or by phone, and we will forward those questions to the expert. And with this, we would like to close our online workshop in September. As a follow-up, we will provide the recordings and a collection of the Q&A as PDF. Thanks again for joining us. Thanks again to all our speakers, and also a big thank you to our QA manager, Klaus Helm, for taking care of the technical support. We hope you could collect some helpful ideas and information from this online workshop, and we are looking forward to meeting you in the next one. We will announce it on time on our homepage and via social media. So have a nice day, stay healthy, and hopefully see you soon. Goodbye.
Bye-bye.